Good afternoon. Sunil, am I audible? Good afternoon and welcome to the second webinar of the series of webinars organized as part of the National Technology Day Celebrations 2022 by KCST in association with the APJ Abdul Kalam Technological University. Today is the second webinar of the series, and today's speaker is Professor Gopu or Potty. He is currently the faculty of the Department of Oceanic Engineering at the University of Rhode Island, where he is currently a research professor. Dr. Potty is a fellow of the Acoustical Society of America, fellow of the Acoustical Society of India, and a senior member of IEEE. He is the chair of the Numerical Modeling, Simulation and Data Visualization Technological Committee of the IEEE Oceanic Engineering Society, and he is editor to several reputed Indian and international journals. He was awarded the Visiting Advanced Joint Research Faculty Fellowship last year by SERP, Department of Science and Technology, Government of India, to conduct joint research at the National Institute of Ocean Technology, NIOT, in India. He was also an erudite scholar of the Kerala State Higher Education Council. Dr. Potty conducts research in the fields of underwater acoustics, acoustical oceanography, marine bioacoustics, and the impact of noise from anthropogenic activities such as wind farm construction and operation. He is a co-author of more than 250 publications, a PI or co-PI on almost 25 research grants and contracts totaling $8 million US dollars in the last 5 years, and he has participated in 10 major research cruises and served as advisor to 20 graduate and thesis and dissertations. Today, Dr. Potty is at a research cruise at sea doing experiments. So since he is currently in the ocean, he has expressed his inability to join as he is out of the internet coverage area. So he has pre-recorded his talk, which will be played now. Thank you all for joining this talk, and hope you'll enjoy the talk. And if you have any questions, I request you to post it in the chat box along with your email ID so that it will be passed on to Dr. Gopu, who will be replying to you. Thank you.
Hello and good afternoon, everybody. Before I start my talk, let me thank the organizers of this webinar series, Kerala State Council for Science, Technology and Environment. The title of my talk is Underwater Acoustics, Unravelling Ocean Secrets Using Sound. This is a pre-recorded talk, and I'm recording this on board the research vessel, Neil Armstrong, operated by the Woodsole Oceanographic Institution. Currently, I'm participating in an at-sea experiment involving multiple universities and multiple research organizations and multiple ships. And as of now, I am within the wireless range, so that's why I'm able to record this. But soon, most likely on the 12th of May, I will be out of the wireless range, and I may not be able to participate in the actual webinar and answer questions. But I highly encourage you to send your questions, if any, to me so that I can answer your queries. With that introduction, let me move on to the outline of my talk. I will start out by highlighting the importance of ocean-related research in general, and then introduce or discuss the question, why should we use underwater acoustics as a favorable or as a tool of choice to do in our ocean research. I will give a general introduction in underwater acoustics and discuss various applications of tools and techniques based on acoustics in ocean-related research with some examples. And in between, I will highlight some of the active areas of research. The picture here shows the a vertical line array being deployed from the Armstrong a few days ago when we were on board. The oceans cover about 70% of the Earth's surface, and oceans have a two-way relationship, back and forth relationship with weather and climate. What I mean by that is that the oceans influence the weather on a local to regional and global scales, while in turn, changes in climate can fundamentally alter many properties of the oceans. That's one reason why we should care about the oceans and how the parameters and processes change over time and how it affects the climate and the weather. Additionally, we depend on the ocean for many of our valuable resources, fisheries, for example, minerals like manganese nodules, petroleum, and recently, more and more offshore ocean-based renewable energy sources are being tapped, including wind, wave, and tidal. So there are multiple reasons why we should care about the oceans. Let's probe a little deeper into the climate aspect. The ocean is increasingly recognized as a mitigator of climate change, and it absorbs about 93% of the excess heat in the atmosphere. The ocean also removed about 30% of the excess carbon dioxide generated by human activities since pre-industrial times. So the changes in ocean temperature and currents brought about by the climate change, as we mentioned in the last slide, will lead to changes in the climate patterns around the world. A warming global climate is affecting the ocean in significant ways through shifts in major currents, like the Gulf Stream, sea level rise, which is a significant problem, especially for coastal communities, and changes in water temperature, pH, salinity, and productivity. The picture on the right, the graph on the right shows the increasing trend of ocean temperature. This is the annual global ocean temperature measured and plotted from 1880 to 2020. And if you look at the recent trend, there is a gradual increase in the average ocean temperatures. So in summary, oceans has become a repository of heat and carbon dioxide. As a result, the ocean is becoming warmer and more acidic. It's also losing oxygen because of the warming of the ocean, which affects the solubility and vertical mixing of the ocean waters. The changes are accompanied by changes in stratification, nutrient availability, surface primary production, which affect the carbon export to deep and food supply at depth. So the primary concern is warming of the ocean waters, and it leads to other secondary effects which are of concern as well. So having sort of convinced ourselves that oceans play an important role in our day-to-day life, indirectly through its effects on climate and weather, let's think about how can we effectively monitor the ocean processes and parameters. What's the best tool to do that? One choice potentially could be light, but if you are deep underwater, you cannot see past your nose. So the visibility is so poor, and light is out of question. So you cannot use light to probe the oceans. There's no light, there is no Wi-Fi, no cell phone coverage, no GPS. There is GPS on the surface of the oceans, but not underwater. Although all of these technologies are based on propagation of electromagnetic waves, which are very poor in performance, which performs very poorly in the underwater because of high attenuation and losses. These include light, infrared, microwave, radio waves, and such. These are all wonderfully efficient in air, but not at all suitable for underwater applications. Underwater, sound is the the tool of choice because it has lesser attenuation compared to electromagnetic waves, and hence it propagates farther distances. People were aware of this very early, and one of the first recorded underwater experiment was done in 1826 when Charles Stum and Daniel Colladon did a simple experiment to measure the speed of sound in water. I think Stum rang a bell held underwater, and Colladon listened to it through a listening tube. And they had a stopwatch which measured the time of travel from the bell to the listening tube. And knowing the exact distance between these two people, they were able to calculate the speed of sound as 1435 meters per second, which was pretty good estimate comparing the crude nature of the experiment. And if you also look at the residents of the ocean, such as the whales and dolphins and fishes, they use sound to communicate, navigate, and explore the oceans. And following their pattern, their behavior, the Navy also use the same technology and techniques and devise sonars for looking for enemy submarines using sound. In addition to the military applications, civilian applications such as seaman mapping, oil and gas exploration, underwater communications are all done using good old sound. So let's take a simple lesson on acoustics and acoustic propagation. The propagation of sound in any medium is defined using the acoustic wave equation. So the propagation follows this equation, and the equation gives you the acoustic pressure P. The sound is a wave, and it is a pressure wave, and it is a propagation of pressure fluctuations. So when I speak, or when a speaker puts out sound, as shown in the figure on the left, the sound in front of my mouth or in front of the diaphragm of the speaker is pushed, creating a high pressure region, followed by a low pressure region when the diaphragm moves back and forth. So there is an alternative high and low pressure scenario, which then propagates along a particular direction. That is shown in the animation on the right. So the source will be on the left end of that brick representation, and so assume that the speaker is on this edge, and it is pushing the medium, creating high pressure and low pressure regions. And as the wave passes, the particles move back and forth, creating a disturbance. So this is called a compressional waves because the wave propagates as alternative compression and rarefaction. Rarefaction meaning low pressure region. So if you look at this equation, back to the equation, if you look at the equation, you have a parameter C there, which is the sound speed, which can be complicated. It can be a function of the space. If you consider a 3D space, it will be X, Y, and Z. And then also time, it can change with time. So it is a 4-dimensional variable. And in addition, the boundaries have influence in sound propagation. And also sound, when hits a boundary, it can reflect. And depending upon the changes in the medium properties, sound can bend or refract as well. So these are the things which complicates sound propagation. Luckily, people have worked on it for years and years and years and come up with very good models which will predict the sound at a particular location, given a source at another location, and also given the speed of sound as a function of space and time as inputs. So that's that part of the research has advanced quite a bit. When you talk about sound, you need to understand the term frequency. In a casual manner, we will refer to this as pitch. So we will say the musician then sings, we say, oh, high pitch and low pitch and things like that. So that technically it is referred to as frequency. The frequency tells you how often an event repeats itself over a specific amount of time. For example, if you stand in a beach and count the number of waves coming in and hitting the beach in a second, let's say the 10 waves came and hit, that means the frequency is 10 cycles per second. Actually, in a real world, that's a high number. Typically, the frequency is 0.1 cycles per second for oceanic waves. So if you, with that understanding of the frequency, you can now classify the whole sound field into different regions. There is an audible band of frequencies. So if the sound has a frequency from 20 hertz to 20 kilohertz, we say that we can hear that, and we say that that's an audible band of sound. Any frequencies within that range we can hear, human can hear. Anything higher than that, higher than 20 kilohertz, we classify it as ultrasound. That's typically used for medical applications, like ultrasound, for example. The frequencies below 20 hertz are very low frequencies, and that's typically where the seismic activities fall under. So you have earthquakes and falls and volcanic eruptions and things like that. So typically we classify into infrasound, audible sound, and ultrasound. And all of these fall under the general umbrella of acoustics. Another important thing to understand when we are working underwater is that the sound speed in the water, it depends on the temperature, salinity, and depth of measurement, or depth of reference, Z. Now, salinity is the salt content, how many parts of salt are present in a particular volume of water. So it is typically the units are parts per thousand. So if you look at the equation for sound in water or underwater, you can see that it's linearly dependent on temperature, the second term. It's linearly dependent on depth, the last term. And at the middle, you have it's also linearly dependent on the salinity, which is represented in parts per thousand. So what that means is that if by some means we can calculate the sound speed in the water, and we can back calculate the temperature using this equation, knowing depth, for example, and salinity, for example. So if you know a couple of parameters, one or more of these three parameters, you can calculate the third parameter using this equation, knowing the sound speed. So most of the parameter estimation problems in underwater sound is aimed at calculating sound speed. And once you have the sound speed, you can go ahead and get an idea about the fluctuations or variations of temperature. And if it is a salinity dominated condition, salinity also. Okay, so with that background and having established or having convinced ourselves that sound is a good option to understand and work in the underwater environment, the next question is, how do we generate sound? How do we receive sound? So we use transducers. Transducers are sensors which convert one form of energy into another form. And when we want to generate sound, we should find a transducer which will convert sound, some form of electrical signals or mechanical signals into sound. So it is typically called a sound source or a projector. It is used to generate sound in water, and they convert electrical energy into sound or acoustic waves. An example is shown here on the left panel. This is the sound source used in an experiment called the ATOC experiment, which is done in 1997. We will come back to this experiment after a few slides. The source had a frequency of 75 hertz. One of the things you have to remember is that at low frequencies, the dimensions of the source will be higher compared to high frequencies in which the source will be compact. So this is ready for deployment, the picture on the left, and on the right is the other scenario where you want to receive sound and convert that into a voltage or an electrical signal. So that's also a transducer. So unlike the source, this takes in the pressure wave and converts that and gives us the electrical signals. That's called a hydrophone. So this is a picture of a standard hydrophone. The lowermost figure here is a fully completed hydrophone, and it has a ceramic element, which is the actual transducer. And it also, in this particular case, has a preamplifier which amplifies the sound, because the sound typically are very, very low in magnitude. So those are individual sources and receivers. Typically, we arrange them in an array or a series of elements, series of sensors connected as a vertical line array, as shown in the figure, the middle figure. on the right panel, or a horizontal line array. With appropriate signal processing, these array configuration will give you increased levels of sound. So you can amplify the sound with appropriate processing techniques. And also, by looking at the arrival time difference of the sound in different sensors, you can also estimate the direction of the arrival of sound. So direction of the source, or the location of the source, which is called beamforming. So this is very similar to what our ears do. So our ears does the beamforming. So if a sound is coming from my right ear picks it up first, and then the sound goes around my head and hits picks up by my left ear, and the brain calculates the difference of time by which the sound arrives in my left ear compared to right ear, and converts that into a direction. Then I can easily say whether the sound is coming from my left or from my right. If the sound is coming from straight ahead, straight in front of me, then both the left and right ear will pick up that sound simultaneously, which will tell the brain that it's coming from front. So it's a similar principle you can use to get the directions. We can design systems where the sources and or receivers can be on the seabed. That's what typically we have. We have a system which is shown on the leftmost figure here, which has multiple hydrophones and another sensor called a geophone, which measures the particle, the vibration amplitude or pressure fluctuation amplitude, in addition to the actual acoustic pressure. Another source which was popular earlier, decades ago, was an explosive source, which is cheap. So basically, you take a bunch of a small amount of TNT and fire it and drop it in the ocean. That will produce an excellent broadband source, but due to environmental considerations, its use is much reduced now. You need to go through a very elaborate environmental clearance to use that. Another option is to make use of advances in technology nowadays in the form of mobile platforms such as gliders, which is shown on the top right, autonomous underwater vehicles, which are shown on bottom right, autonomous surface vehicle, which is shown on bottom left, and remotely operated vehicle, or ROVs, as shown in the top left. So you can attach your sources and or your receivers on any of these platforms and make measurements with appropriately programming the platforms. A couple of issues related to this. One is the self-noise of the platform that can create problems. The second and more important problem is the difficulty in finding out the exact location of these platforms. As far as ASV, or autonomous surface vehicle, is concerned, you can use GPS fixes continuously to keep the location, to maintain, to get the location information. So there's no problem there. For these two, gliders and AUVs, the location information can only be obtained intermittently when they surface. So you get a GPS fix when the vehicle surfaces into the ocean surface, but otherwise, when they are underwater, you are blind. You don't know the location. For remotely operated vehicles, they are tethered to the mothership, So you have a reasonably good estimate of the location. So these are becoming more and more popular now because of the flexibility it offers to make continuous measurements, especially in areas where a ship cannot easily go, like in shallow water regions or locations where locations which are hostile, not friendly locations. In those kinds of scenarios, the AUVs and gliders are becoming popular. These are some pictures from our own earlier deployments. This was done in East China Sea. Here we are deploying a vertical line array, which was hung from the ship. On here on the left side is me, a picture of me. This was done in 2000, so 20 years ago. This is on the right, in the same experiment. The Chinese were able to drop explosive sources because it's Chinese waters. So they were dropping explosives by hand in water. So let's move on to some applications. So let's start with echolocation because that was probably the earliest application of acoustics in an ocean-related problem. The problem was triggered by the Titanic incident, and people started thinking about some tool which can look ahead and tell the operator of the ship that there is an obstruction. That led to the development of echolocation or echo ranging, a technique for detecting distant objects by sending out sound and listening to the echo, which is similar to what the bat or the dolphin and later on the submarine does. So they all send out sound pulses and receives, and depending upon the time difference, they estimate the distance at which its prey or an obstruction like a beach is present. The principle, if you turn around this picture into a vertical dimension, you get echo sounder, which is used by ships to find out the depth of water. So they have a sensor underneath the ship, which sends out acoustic pulses down towards the bottom. It hits the bottom, gets reflected, and then it's received at the sensor. So you can find the time of travel, knowing an approximate value of the sound speed in the water. You can easily calculate the depth of water in that case. So identification, localization, and tracking. Those are the three principal problems that Navy is interested, and also many civilian applications are interested in underwater. They are typically done with the in this manner with travel time, or you can also use the amplitude of the signal or signal measured, or other processed and derived quantities such as coherence, dispersion, waveguide invariant. There are multiple derived quantities which can be used to calculate the range and identification problem or localization and tracking problem. Now keep this picture in mind, the echo sounder. If you take that picture and invert it, you get another instrument called inverted echo sounder. It's a very popular instrument because of its simplicity, because echo sounder has a very long history of good performance. So you take that and you turn it around and keep the sensor in the sea bottom and send the signal upwards. It will hit the water surface and it will come back. And knowing the depth, knowing the depth, and using the equation for sound speed I showed earlier, you can back calculate the temperature as a function of depth using the travel time information. So the inverted echo sounder works on the same principle as the echo sounder, but the measured quantity or the inferred quantity or the estimated quantity is not the depth, but it is the temperature or some other quantities. So acoustics offers an efficient tool to estimate ocean parameters and processes such as the temperature and sound speed in the water, etc. Many acoustic-based instruments have been deployed to measure temperature, salinity, bathymetry, bottom layering, and properties. We talked about echo sounders, we talk about inverter echo sounders. The other civilian measurement platforms include side scan sonar, which gives you images of the sea bottom. There is a sub-bottom profiler, which gives you the layering information, layers in the sea bottom by measuring, by sending sound beams into the seabed. All of them work in a similar fashion or similar principle, either using travel time or using the amplitude of the echo. Another instrument that we have is this instrument, which is on the bottom right, which is collision bottom recorders. It is a self-contained measurement system, which includes a hydrophone, which measures pressure, in addition to an accelerometer type instrument, which measures the velocity in three mutually perpendicular directions. So this is on the top. It is the OBX is shown getting ready for deployment, in addition to the geosled, which I mentioned earlier, in a location near the wind farm of Virginia, of the east coast of United States. The reason why we use this XY Z vibration, acceleration, that'll become clear towards the end of this presentation. So, turning back to my research over the last 20-25 years has been focused on using sound to image the oceans and sea bottom, just like we take images of our body using X-rays or CAT scans. The principle is the same. The basic principles of this, the technique that I use and many of my colleagues use, is closely related to that used for CAT scans. So essentially, we try to produce a map or a slice through the bottom and the bottom column to give you maybe various layers of variation of various properties as a function of space and sometimes time. So this particular slide gives you an overview. I won't go too much into the details. I have the primary reference in the bottom. So I mentioned that once you know the sound speed, once you know the sound speed in the water column as a function of space and time, you can solve the wave equation and calculate the pressure. Very good acoustic propagation models are available to do that. So that's called the forward problem. Given the input parameters, predict the acoustic pressure. So many investigators, including me, are interested in the reverse process or the inverse problem, which means given the acoustic pressure, measured acoustic pressure, how can we calculate the sound speed as a function of space and time? You can do this iteratively. So basically put in different values for sound speed, run the propagation model, calculate P, and compare it with the actual measured P, and keep on changing the value of C until the measured and the calculated acoustic pressures match. And that's essentially the crude way of describing this flow chart here. A couple of differences. I don't use the actual pressure, but I use a derived quantity. So this is the actual pressure shown on the top left. The next to it is the derived quantity, which is called the group velocity or group speed dispersion, which I get using some fancy signal processing technique called time frequency analysis. And then I assume values for C, the sound speed, and some other parameters like the distance between source and receivers, water depth, etc. And then run the propagation model, calculate the acoustic pressure, compare it, create the predicted dispersion, and try to match it. So until I get a final match, I keep on changing the input parameters, and the input parameters which produces a perfect match will be a perfect or close to perfect or acceptable match will be the final answer or the estimate. So this is technique became very popular. I developed this in 2000 as part of my PhD, and it became very popular, and it's still being used extensively in our community. A variant of this will be acoustic thermometry for ocean climate, or ATOC. Acoustic tomography uses travel time, so they instead of using the dispersion, they use travel time of sound in the ocean to measure the temperature. So instead of measuring the sound speed, they go one step further and convert that into a temperature. And also they use very low frequencies, and they send sound over very large distances. When I say very large, like hundreds of kilometers. Low frequency meaning around 75 hertz sampler frequency. They have done this successfully, demonstrated this. The test, this ATOC experiment verified that transmissions broadcast over many years. Basically, they continue to do that over years and years and years, so that you can measure long-term changes in ocean temperature and then try to see whether that correlates with climate change. A variation of that will be a similar technique, which uses, instead of using an active source like an acoustic source, uses seismic energy, which is almost always present in the ocean, uses that to replicate this algorithm and come up with an estimate of the ocean temperature. So that is called seismic ocean thermometry, which is a recent experiment, and the results were published very recently in 2020. So, having talked about all these things, I should also mention that ocean is not a quiet place. There are a lot of sound sources present in the ocean: marine mammals, humans who make a lot of noise through the use of sound for various applications I mentioned earlier, in addition to ship traffic, which is a dominant source. And then there are natural sources of sound like waves, wind, rain, earthquakes, seismic energy, and all these things. They all are present at any time, at any location, which is called the ambient noise, and the general terminology we tend to use is ocean soundscape. So listening to this ocean soundscape helps us to understand how ocean physics and biology of marine communities are responding to a dynamically changing ocean. So the idea here is that you continuously measure and analyze the ambient noise in the ocean or ocean soundscape over a long period of time at a certain location. And any change in the ocean soundscape over a period of time can be correlated to some changes in what is happening within the community, which creates that soundscape. So that's the idea here. I talked about, I forgot to add ice melting. If you are in the Arctic, one of the major sources of noise is ice. So when ice melts and bubbles are produced, you get a certain type of noise, called ice battling noise. hope you can hear that. And when large chunks of ice falls off from glaciers, you get a noise like this, which is called ice carving noise. So the soundscape in the Arctic will be dominated by these these noise sources. And if you continuously monitor the ambient noise or the soundscape in the Arctic, you can look for clues of the presence of these kinds of activities over a period of time. So that's the idea. Another thing, if you are again in the Arctic, you need to be careful is the increasing ship traffic. The global warming melts sea ice, and it opens up the shipping routes in the Arctic. So there is more shipping activity in the Arctic nowadays. So that's an important noise source, and it has been measured. It has been reported that the ambient noise has increased by as much as 12 dB above the natural background level in some location. So this also will form part of the soundscape change in a soundscape study if you are doing that in the Arctic. So in summary of that particular topic, a climate-induced change in species like fish or marine mammals can also produce change in the soundscape, but you have to view that in the context of other changes in the soundscape like shipping and if you are in the Arctic ice melting. But generally, the soundscape is an interesting tool to remotely sense both climate change and shift in the ecosystems. So we can listen to the underwater conversation using passive acoustics to assess marine biodiversity, animal density, and ecosystem status and health. So that's the bottom line. And you can do this in a relatively cheap instrumentation using simple hydrophones and recorders. And you can do it over a long term to monitor changes in the ecosystem. A new tool that could be useful in future will be the distributed acoustic sensing technology, which uses fiber optics cables. So the communication companies have laid out kilometers and kilometers of fiber optics bundles in the ocean floor, and they don't use all the individual fibers. There are some spare ones, and you can use those spare ones to do the same type of soundscape analysis that we mentioned in the previous slide instead of using hydrophones. So you need a system called interrogators, which sends out a laser pulse into these individual fibers, and then measure the backscattered energy and correlate that to a change in strain in the fiber. And you can then correlate that change in the strain to a measurable, such as a vibration or sound. So this particular technology is getting more and more interesting, and more applications are coming online. Finally, another recent entrant into the soundscape is offshore wind farms. So if you look at the figure here, these are the proposed wind farm developments in the US East Coast, and you can see that there are plenty of them. The estimated potential, the technical or available potential is around 2,000 gigawatts in the US East Coast. By 2017, they are planning to tap 24 gigawatts. And there are a couple of wind farms already are functioning in the US East Coast. I mentioned a system which we developed to measure the particle, the accelerations on the seabed. The reason we did that was we were monitoring the wind farm construction and operation in the US East Coast. And one of the things that some fish biologists requested us to measure was this particular measurement of particle acceleration, because apparently fishes are sensitive to particle motion. They have something called otolithic organs in their ear, and these organs respond to particle motion. So the question then is, even when the sound is small, if particle velocity or particle motion is high, fishes will get affected, potentially will get affected. So we measured the data, and these are results. I won't go into the details, but what we see here, the black line is the measured particle acceleration, and the colored lines are the threshold of sensing at which the behavioral change occurs, or threshold of behavioral change of different kinds of fish. And the left panel here shows the measurement in water, or right panel shows the measurement on the seabed. And one important observation that we made based on that result was that the particle motion levels are much higher than the threshold on the seabed. The conclusion we derived based on that measurement was that the fish and other creatures which live on or close to the sea bottom will potentially get affected, and their behavior could potentially change. This was during construction, while during the operation, the levels were the actual levels produced by the operation was much lower, except at one particular frequency here in water. So the levels doesn't rise to the level of behavioral changes in the fishes. With regard to sound, the sound levels during construction, which is shown in the black here, and the during operation, which are shown in the red level, red curve here. During operation, during construction, the levels are much higher than the threshold levels, which are shown on the left panel. But during operations, it barely exceeds or barely reaches the level of behavioral change. So just before concluding, let me just point out that there are other application technology developments, such as acoustic sensing of population distributions of fish, whales, and plankton. Tagging of fish and marine mammals is a big area of activity. So you tag the animals and then track them using different receivers. Thermometry, we discussed that earlier. Acoustic quantification of air-sea mixing and material exchange. Acoustic measurements of polar pack ice thickness, which is significantly important in Arctic region. And one big area which I avoided discussing was acoustic communication. Acoustics or sound is the major tool for communication underwater, and that's a huge area of research. Having preached the benefits of acoustics in an ocean environment, I should also point out that it's a challenging environment to work with. It's an unstable working platform because of the rocking and rolling. It's costly. Typically, a research vessel like the Armstrong costs around $50,000 per day. Longer execution time. Everything takes a long time. Tough working condition. And equipment failures go hand in hand with ocean environment. In addition to that, the ship-based research activities is sometimes becomes difficult to access. Limited access to limited access areas such as hostile areas and shallow areas and things like that. Some of the problems, tough weather, which is shown in the left panel here. In winter, snow and bad weather, and then occasional hurricanes are shown in the top right here. So this is the top right is in 2006 when we were doing some experiment in the US East Coast. The figure on the left with a wave banging on the deck is in 1996, another experiment in the US East Coast. But not always. Occasionally you get excellent calm conditions, enjoyable conditions, and sometimes you get company in the form of dolphins and whales circling and hanging out with you. So with that dolphin vocalization, I will conclude. And I'll be happy to take any questions. Unfortunately, most likely it will be remotely with a delay. So with that, I conclude my talk. I hope you enjoyed the talk and you learned something out of it. With this warm sunset from RV Nor, this was in East China Sea in 2000. I hope rest of my experiment in this cruise will be something like this. So with that, I conclude, and I thank all of you for listening, and thank again the organizers for their invitation. Thank you very much.
Thank you, sir. If there are any questions, kindly post in the chat box along with your email. Sir will be responding to your questions, and he'll be replying to your email, individual email IDs. If there are no questions, we'll move on to the conclusion. Respected Professor Gopu or Potty, other distinguished senior scientists attending the lecture, and dear participants. We were well introduced to ocean acoustics and the acoustic environment in the ocean, the oceanographic tools that are being employed by Professor Gopu to the audience or to the participants. He has highlighted the importance of ocean and ocean research and how acoustics can help us in ocean research, and the importance of acoustics in oceanography. Thank you, sir, for introducing us to a very not novel topic, but a topic of contemporary importance, which we normally wouldn't venture into. So thank you for introducing the topic. And thank you also for recording your talk and sending it over to us, because we all know that you are in the sea cruise doing experiments and trials. So even amidst your inconvenience to attend the program, I appreciate the interest you had shown to record the talk and send it over to us so that it can be telecasted here. Thank you, sir. Thank you for your cooperation, and looking forward for future technical talks also. And tomorrow also we have a technical talk that is given by Dr. Ajit V. Pai from Jaguar Land Rover about electric vehicles and their energy management. I request all the participants to be present tomorrow also at the same time, 4 p.m. Tomorrow's is the third webinar in the webinar series organized as part of the National Technology Day celebrations 2022 by KCST and APJ Abdul Kalam Technological University. I thank all the participants who have attended the program. I hope you all got benefited from the program, from the technical talk. Thank you all. Thank you once more. Thank you.